Right, so this is going to be a short video on how to do molar gas volume calculations. It's only going to involve a little bit of theory at the start and then 2 example practice questions. So, when dealing with these type of calculations, we're dealing with volumes of gases, and you need to know that 1 mole of a gas occupies 24 decimeters cubed, provided you're at room temperature and pressure. So 24 decimeter cubed is, well, I find it very difficult to think about what a decimeter cubed actually looks like. So I mean, it's just another way of writing litres. So that's quite a big volume. That's 12 2-litre Coke bottles. So that's 1 mole of gas. Now it doesn't matter what the gas is. And that might seem a little bit strange to start with, but in this diagram here I've got a diagram of a monoatomic gas. So in other words, a gas that exists just as atoms. So an example of that might be helium. So these could be helium atoms, okay, in this container. Now if the gas was a slightly bigger or heavier gas, so helium's right at the top of the periodic table. It's probably one of the very smallest gases. Let's imagine we've got oxygen, which is slightly bigger in terms of atoms, and it's also diatomic. So we'd have another atom bonded there, another atom bonded to that one, another atom to that one, another atom to there. There, you get the picture. Okay, there's my final atom bonded there. So we've now got, instead of 8 atoms, we've now got 8 diatomic molecules. And these 8 diatomic molecules don't take up any more space than the 8 atoms. And that's because there was so much space in between the atoms originally, in here, that it doesn't matter if we bond another atom onto the original atom to make a molecule, because it's just occupying the space that was empty to start with. If we turned it into water vapour, so it would be H2O, so there's the oxygen in the centre, we bonded a hydrogen here, hydrogen bonded there, hydrogen bonded there, and so forth. Again, you can see all we're doing is filling up the space between the molecules. The actual substance is not going to take up any more room. So it doesn't matter what the identity of the gas is, provided you're at room temperature and pressure. 1 mole of the gas is going to occupy 24 decimeters cubed. You also need to know how to convert between decimeters cubed and centimeters cubed, which I hope you already know. So 1 centimeter cubed is 1,000th of a decimeter cubed. So in other words, 1 decimeter cubed is 1,000 centimeters cubed. And again, when I'm teaching, I ask students to think of a centimeter cubed as a milliliter and a decimeter cubed as a litre. It just helps me actually to visualise what it actually looks like. So 24 decimeters cubed, well, if 1 decimeter cubed is 1,000 centimeters cubed, 24 decimeters cubed is going to be 24,000 centimeters cubed. And you'll be given this information in the exam. So the question will follow with that bit of information. You're expected to be able to use it. So let's have a look at what a question might look like. Okay, so this question involves the decomposition of hydrogen peroxide. Now this reaction is on the syllabus because we use it to produce oxygen, and you should, I hope, know the catalyst for this reaction, and you could be asked for the catalyst. So the catalyst which causes this reaction to occur very, very quickly is manganese oxide or manganese dioxide. Quite often when marking scripts you see students putting magnesium oxide, but it's a different element. It's manganese oxide. So it's got the formula MnO2, and it's a black powder, and if you've got your peroxide, you add the black powder to it and you immediately see very, very vigorous effervescence, and that's the oxygen coming off. Now, it looks, when you look at the question, like you haven't been given very much information. All they've asked you for is the volume of oxygen, and they've said that you've got 17 grams of hydrogen peroxide. So again, I'd approach the question just like you've done all the other moles questions, and we're going to do it in 3 stages. But before we do anything, we're going to organise our information. So here we've got 17 grams of peroxide, and we're going to try and work out the volume of oxygen. Now, you might want to have a go at this before you go any further, so pause the video and have a go. I'm just going to carry on with the calculation. Now, the first thing we do before on any moles calculation is convert what we've got, or what we know, into moles. And that's the first stage. So we've been given 17 grams of hydrogen peroxide, and hopefully you'll remember the way to convert moles or mass into moles. So we use a triangle. Moles is mass over the relative molecular mass, or the mass number, or whatever you want to call it. So we've got moles of H2O2, and so moles is mass divided by Mr, as a student I spoke to the other day called it. So we've got 17 grams over. Now you'll need your periodic table for this, so have a look at what hydrogen weighs. So hydrogen, each one weighs 1, and oxygen, each one of those weighs, now there it is, 16. So we've got 2 hydrogens in there, so 1 plus 1 plus 16, and there are 2 oxygens, that's meant to be 6. So that works out to 17 over 34, which is 0.5. And that's the end of stage 1 in our calculation. So the moles of hydrogen peroxide is 0.5. Now, as usual, we convert the moles of the substance we've got into the moles of the substance that we want. Now we want oxygen. So moles of oxygen equals the moles of the substance we've got, H2O2, times want over got, which is a quirk of my teaching, but as I've used that in all the other videos, I'm going to stick with that recipe. You could just do this middle step using a ratio, which effectively this is, but it's just a slight strange way I have of working it through. So you've just worked out your moles of hydrogen peroxide, which is 0.5. The substance we'd got was H2O2, so the got number was 2. And the substance we wanted was oxygen. There's no number there, so it must be a 1. So 0.5 times a half is 0.25. And that's our second step done. So the moles of oxygen is 0.5. Now we need to convert moles into volume of oxygen. And we've not done this before. Now we know that 1 mole of oxygen is going to occupy 24 decimeters cubed. So 1 mole O2 equals 24 decimeters cubed. But we've not got 1 mole, we've only got a quarter of that. So as we've got 0.25 moles of oxygen, it's going to occupy a quarter of 24. Excuse me, I've got a cold. So 24 times a quarter, which comes out as 6 decimeters cubed. And that's it. That's a gas mole calculation. I have seen people use a triangle for the gas volume, So rather than using that method, they would use this kind of triangle up here, where you have moles and then volume on the top, and then if you're working in decimeters cubed, 24 down there. So if you were going to use that triangle, so volume is moles times by 24, so your moles is 0.25 times 24 gives 6 decimeters cubed. I have to admit that I would work it out using that method, okay, but I have found that students prefer to use a triangle, but it does mean that you have to learn the triangle and get it right in the exam. So, final question, we're going to this time start with a volume and turn it back into mass. So 36 decimeter cubed of methane. I do have trouble with my sixes, don't I? 36 decimeter cubed, and we're producing what mass of water? Same as normal, first thing, convert your substance that you've got information on into moles. So this time it's a gas, so we're going to use the gas triangle, just because that's what I find students prefer. So moles, volume 24. So moles of CH4 equals 36 over 24 using that triangle, and that gives 1.5. End of stage 1. Right, so this is the moles of the substance we got, this is the substance we want. So moles of water, you may have noticed I'm doing this a little bit quicker because I'm running out of time on the video. So moles of water equal moles of methane times want over got. So that's 1.5 times the substance we want, so our want number is the 2 here. The substance we got was the methane, and that number there, well, we haven't written the number, so it must be 1. So 1.5 times 2 is 3. End of stage 2. Now, the question has asked us for mass. And we've got moles of water, so we're going to have to use the mass triangle, so moles, mass over Mr. So mass is moles times Mr. So the moles are 3, and this is the mass of water. So we've got 2 hydrogens, so 1 plus 1, and oxygen, find that on the periodic table, that weighs 16. Yeah, see, I can't write my 6's. So it'll be 3 times by 18, and that comes to, just working that out in my head, 54 grams. So a little bit of a whistle-stop tour through that question, because I'm running out of time. Convert the moles of the substance you got, which was methane, or convert the volume into moles. Then use your mole ratios, or the want over got method, to find your moles of the substance that you want, and then convert the moles of the substance that you'd wanted back into what the question had asked for, which was mass. And that concludes the video.